Hello and welcome to the lectures on state space approach to control system analysis and design. In the last few weeks, we have learnt about standard state space representation of dynamical systems, mathematical modeling of physical systems and expressing them into standard state space form, solution of state equations, simulation, controllability and observability, and stability. Now we embark in this week upon a new topic, which is control analysis, control design via desired closed loop response. We in the conventional control approach, the objective of control design is to achieve performance in terms of time domain specifications such as the peak overshoot, settling time and steady state error. You might have come across the response to step input of prototype second order system, which we used to plot something like this. Let us say this is the input ut. Let me correct this, a little error into plotting. So this is the time axis, of course, and this is in response to a step change in input. The system, suppose it behaves like this. So this is the output yt, and versus time, this is the reference line where the output should reach. Now generally the specification of system can be given in terms of this peak overshoot, how much it is, the settling time when it reaches in some band like 2% or 5%. So the time when it enters this band and remains in that band, that settling time, and the steady state error. For example, I have tried to show that the output remains little less than the expected output when time tends to infinity, when the time becomes very large, and this is the steady state error in response to the step change in input. So in conventional control, the control objective has been to achieve a desired performance specified in terms of such parameters like peak overshoot, settling time, steady state error, rise time, etc. Other way in conventional approach, the specifications were given were in terms of frequency response specifications. For example, the resonant peak or the gain margin and phase margin and bandwidth. So you might have come across this kind of a plot, this kind of a plot where this was being shown as the resonant peak. This is the system gain and this is the frequency. This is the magnitude of the system gain. So many times the specifications were given in terms of this resonant peak and the bandwidth. Bandwidth means that where the gain is 0.707 times of the maximum value, and sometimes in terms of gain margin and phase margin. You might have come across plot frequency domain plots, for example this one. So this is the 0 dB axis, and the gain has gone below 0, and at the phase crossover frequency, this frequency is phase crossover frequency, there we read this, and that is the gain margin. So the specifications could be in terms of such frequency response specification parameters such as the gain margin, phase margin, bandwidth and resonant peak. These were the things in the conventional control. and the control system is assumed to be unalterable. Basically, this is the control and this is the system. This is the controller, this is controller and this is the system, and always the aim of control design has been to get the controller, and nothing is done to the system. It is assumed that no changes can be made in the system design. The system is already designed along with its various entities, subsystems, actuators, sensors, etc. So only possibility is to do something with the controller, the control system. So with those objectives, the design is to make a suitable controller for getting the desired performance specifications, either in terms of time response or in terms of frequency response. And usually a cascade compensator is put in the forward path before the control system like this. So this is the feedback of output coming to the input side, which is compared with the reference, and error signal has been generated, and that error signal enters the cascade compensator, the output of which is the control signal, and the cascade compensator is so designed that the control signal will vary in a manner so as to affect the output and the desired specification parameters will be achieved. That is the idea. So this compensator has to be properly designed, and the form of compensators that were considered in conventional control are, for example, a lead compensator, which was used to get the desired transient response, a lag compensator to correct to achieve steady state error characteristics, good steady state error characteristics, or a PID type to achieve both good error characteristics. For example, by an integrator, the error could be corrected. By introduction of derivative, the time response could be made fast, and so on. So the compensator of a lead type or a lag type or a PID is put in cascade with the system under control, and thereby the response used to be achieved. Now, one thing that characterizes the conventional methods is that the solution approaches are generally graphical, over and above iterative, and mostly the solution so obtained is non-exact. So if more iterations were performed, design were done again and again, then it could go to the required design specification, it could achieve the required design specifications. However, the solution is not one attempt and non-exact solutions are only obtained. In contrast to all these things, in modern control, the design is carried out with the two types of objectives. One objective is achieving a desired specified overall transfer function or model, and the methods falling into this category are called as pole placement methods. The other objective is to minimize an integral performance index, and the methods falling into this category are called as optimization methods. So in modern control, the design is carried out in terms of this: achieving desired transfer function or minimizing an integral performance index. And in contrast to the conventional approaches of design, the solution approaches in modern control are computational, and they lead to exact solutions, one-shot exact solutions in most of the situations. Sometimes iterative, but most of the time they lead to exact solution without iterations. With iterations, of course, in this case also, the control system is assumed to be unalterable. No changes are possible in the system which is being controlled. So everything is being done is for the controller. The controller is to be designed, or in the conventional approach, the compensator was to be designed. So in this chapter, we will learn the pole placement methods, and as brought out here, the pole placement methods, the objective of design is to achieve a desired overall transfer function. In fact, in pole placement, we try to get a characteristic equation, a specified characteristic polynomial or equation. So we proceed ahead with that, and before actually going to handling the design, in a few slides I have to explain the concept of output and state feedback. So in the conventional approach, let me recall that a system used to be described something like this. This is the input, the U, and this is the output, the Y, and this is the system which was mostly represented by a transfer function GS. Now in this, these internal variables are not visible. In case of state feedback approach or state space approach, the system representation is like this. You can see that inside the GS we may have this. So essentially these mathematical equations, they are shown here like this. The input enters, multiplied by B, enters this adder, and to that adder the state of the system xt multiplied by A enters. Sum of these two make dx by dt, and integrated, that gives x, the state. The state multiplied by C gives the output. So what we see inside these dotted lines is the internal representation, and the state, that is where we have shown the state. And this graphics, this is the block diagram representation of this set of equations, this state equation and this output equation. They are represented graphically like this. Now we have n state variables, m number of inputs, and p number of outputs. Now in this, if we take this output, if we tap this output, and through a gauge K and this control law, we feed it back to the input terminals like this, as shown here. So there it is compared with the reference R, and the difference of two is usually the input U, which enters the plant. This is the plant, and thereby the output will behave probably in the desired manner as K has been chosen. This K is called as the output feedback gain, and this equation is the control law with the output feedback. Here the K is the feedback matrix. It has, you can see, the same number of rows as the number of inputs. So it has m rows and it has p columns. So U1 will be K11 Y1 plus K12 Y2 and so on up to K1P YP. U2 will be K21 Y1 plus K22 Y2 and so on up to K2P YP. So this is a M by P matrix. and this is the, as I told, this is the control law with the output feedback. So this is the structure of output feedback system. The state feedback system looks slightly different. Here we tap the states. This is the state of the system xt. In this case we tap the states, and states through a feedback gain matrix K, they are brought to the input terminals. They enter this comparator where difference of RT and this K times XT is generated and fed back to the input terminals of the system as the input U. So here the control law is this. UT is minus K XT plus RT. Difference is here. Earlier it was Y here and here it is X. This is state feedback and that was output feedback. And the difference is in the size of this matrix. It has M rows and N columns. More elements than the other one because the number of outputs is comparatively much less than the number of states of the system. So this is, in this case, in the state feedback case, there are still M inputs, but this matrix has the size M by N. Input U1 is K11 X1 plus K12 X2 and so on. Earlier it was generated based on the outputs. So the difference is that here the control is generated based upon the states, and this is the state feedback controller. This, as we know, the outputs of the physical systems are easily available for feedback, and thus a output feedback system is easily implemented, can be easily implemented. However, states are internal variables. Only a few of the states may be coming at the output terminals. Many of the states cannot be measured. There is no direct way to measure the states, the internal variable of the system. Or even if it is possible to measure, putting instrumentation for all the states will be a very costly thing to do. So generally not all the states are available for feedback. Either they cannot be measured or they are not measured for economic and other reasons. So state feedback is difficult to implement. However, there are methods. Observers or state estimators can be designed. In that case, state feedback can also be implemented, but it increases the complexity. But there are advantages because all design specifications can be met with the state feedback. We will see how. Whereas the output feedback has limitations. It doesn't achieve all the specifications. So we see how the state feedback can meet all the design specifications. With the help of one illustrative example which is here, we consider a system described by this transfer function 6 by s, s plus 3, s plus 10, which can be written like this, factored form, and these three are put in cascade like this to represent it by this block diagram. This is the block diagram of this system. So US is entering to the first block, first subsystem, which is 3 by s plus 10. Its output is x1, and that is the input to the second block, 2 by s plus 3. Output of this block is x2. I'm sorry, this is x3, this is not x1, excuse me. So this is x3. And this is x1. The output is the same as the state x1. It is coming from this block, input to which is x2. x2 itself is the output of this block, to which the input is x3, and x3 is output of this block, to which the input is ut. And this is the whole system. These are internal to the system. So x1, x2 and x3 are the internal variables of the system, and they are state variables. So x1, x2 and x3 are state variables. They are being fed back through the state feedback control law, which is this. K times x in this case is k1, k2, k3 times x1, x2 and x3. So that gives k1 x1, k2 x2 and k3 x3. This is the control law. Now this is represented by this block diagram. This x3, again let me correct, this is x3s. This x3 is brought out through a gain k3, x2 through a gain k2 and x1 through a gain k1. And they are added together to get the feedback signal. This is minus kx, and then difference of r and kx is us, that is driving the system. Now this block diagram can be manipulated to achieve this block diagram. What has been done, that this k2, through k2 this x2 was being taken, that has been brought outside this block, after this block 1 by s here. And similarly this x3, which was tapped through gain k3, that takeoff point has been brought here. And so those blocks are modified. Instead of k2 it becomes k2 divided by the transfer function this, so it is k2s. And this takeoff point has been moved here, so we have k3 divided by this transfer function and this transfer function, so we have this. Now all these three can be combined together, and the representation of the system which was originally shown reduces to like this. And now one can obtain the closed loop transfer function, which will be this. The closed loop transfer function, when it is derived from this, which is g by 1 plus gh, of course gs by 1 plus gshs, it will be this. And what we see, compared to the open loop transfer function of the system, this is the open loop transfer function of the system if feedback was not introduced. We see that the coefficient of s square here is 13, here it is 13 plus 3k3. The coefficient of s is 30, here it is 30 plus 9k3 plus 6k2. Coefficient of that constant term was not there, the constant term here is k1. So what we see, that the coefficients of all different powers of s in the denominator or the characteristic polynomial have changed, and they have become dependent on k1, here k2 and k3 and k3. So through a suitable choice of or appropriate choice of the gains k1, k2 and k3, this denominator of the system can be changed, the transfer function can be changed, and all coefficients can be changed based on k1, k2 and k3, and any choice will be possible. So based on state feedback, the characteristic polynomial of the system or denominator of the transfer function can be arbitrarily changed, meaning that the poles can be arbitrarily assigned. Whereas if we go for output feedback, which is shown here, only one term will change and remaining terms cannot change. This 13 will remain 13, this 30 will remain 30. Compare with this and compare this with this. So because of the output feedback, only one term could change. So obviously there will be limitations in the way the characteristic polynomial of closed loop system with output feedback could be. This example illustrates that state feedback is much more effective, much more powerful compared to output feedback, as it can change all the coefficients of the characteristic polynomial. Output feedback cannot. This now we come to how to design the state feedback, and for this we consider the general linear time invariant system given by the matrices A, B and C, this state equation, this output equation. It has n states, m inputs and p outputs as it was told in the beginning, and we have this control law. This is the state feedback control law, and the aim of the design is to fix the matrix K, to design the matrix K such that closed loop system poles are at desired locations. So system matrix A has poles at some locations. With those poles located at those locations, the system behavior is not probably as desired, and desired system behavior will be obtained if closed loop poles are located elsewhere, which we call as desired locations. Then the system will behave the way we want, and for that we want the gain matrix to be obtained in this control law. Once K is obtained, then we can see that design has been done. It has only to be implemented. So what will happen once this state feedback is incorporated with this system, means in place of u, if we substitute this expression, we get the closed loop system dynamics as this: ax, that comes here, and b times u, it becomes like this because u is minus kx plus r, and this simplifies to this, and in that we put the notation AC equal to A minus BK. So this AC will be called as the closed loop system matrix. A minus BK is the closed loop system matrix, and the open loop system matrix was A. So closed loop system matrix depends on A and of course BK. The gain K is to be chosen. If gain K is available, then AC behaves differently than A. Its eigenvalues will be different than the eigenvalues of A. So the characteristic equation of the closed loop system will be this. The coefficients are alpha 1, alpha 2, etc. And they will in general be functions of the gains K1, K2, etc. up to Kn. So what we can do is that we can equate these coefficients to the coefficients of the desired characteristic polynomial of the respective powers of S, and then we will have n equations for n quantities to be solved, and so K1, K2, K3, etc. up to Kn can be determined from those equations, and thus we will have the knowledge of K. This is illustrated by a design example. So we are given with this system. This is the A matrix and this is the B matrix. Of course, we are considering single input situation, and we want to obtain a K in the state feedback control law U equal to minus Kx plus R, so that the closed loop poles are at minus 3, minus 2 and minus 1. We want to design K. We have to obtain a K. So we proceed like this. With these pole locations, the desired characteristic polynomial will be this: the product of three polynomials of degree 1, s plus 1, s plus 2, s plus 3, and this product will give this polynomial of degree 3, which is s cube plus 6s square plus 11s plus 6. and this A is there, this B is there, K will be K1, K2 and K3 like this. So BK will be, the product BK will be 100 into K1, K2, K3. So 1 times K1 is K1, 1 times K2 is K2, 1 times K3 is K3, and 0 times K1, K2, K3 will give this 0 row, 0 times this 0 row. So BK is equal to this. And so A minus BK will be, this is A and this is BK, and thus we get this matrix. So because this BK has 2 0 rows, so the 2 rows second and third rows are same as the rows of matrix A, and first row has changed as 6 minus K1, 1 minus K2, 2 minus K3. Now we obtain its characteristic polynomial. So we have this as Si minus AC, and the corresponding characteristic polynomial will be obtained like this. So we calculate basically the determinant of Si minus AC, and after some simplifications we will get this. Now we have to compare these coefficients with the coefficients of desired characteristic equation, which we obtained was S cube plus 6S square plus 11S plus 6. So this will be equal to 6, this will be equal to 11, and this will be equal to 6, which is written here. We get these three simultaneous linear equations, and when we solve them, we get K1 equal to minus 3, K2 equal to 1, and K3 equal to 2. And thus we have the solution of the state feedback gains. So this is what was narrated before taking up this example, that the AC matrix, AC means that closed loop system matrix, which is A minus BK, will have terms containing K, and so the characteristic polynomial of the closed loop system matrix will have various coefficients containing K. By comparison of the characteristic polynomial, which is containing K at different terms, with the desired characteristic polynomial, we will get n equations. N is the number of gains to be obtained and also the order of the system, and so n equations can be uniquely solved for n gains. It gives a unique solution, and so this solution gives the control law which will achieve the poles at the desired locations. So this is how the design can be carried out. However, if the system matrix, the description of the system is available in companion form, then the design task is particularly very easy. This is a companion form representation. This was introduced earlier. In this part of the first column is 0, except the last element, all elements are 0. This n minus 1 times n minus 1 part is an identity matrix, and the last row is containing the coefficients of characteristic equation taken in the reverse order. This is coefficient of s power n minus 1. Next will be the coefficient of s power n minus 2, and so on. This is the constant term. This is coefficient of s. So this companion form system matrix has the coefficients of characteristic equation appearing in the last row with minus sign, and B matrix has a unity here, remaining all elements are 0. This is the structure of companion form matrix. Now if the system design is available in companion form, then the control design task is very easy, because when we look at B times K, we see that because B is all zeros, last one is 1, and K is K1, K2, etc. So when we multiply, we get this. In this part is 0, this part is identity matrix, and the last row is the K matrix, this K matrix. That means BK is also in companion form, and the original matrix A is in companion form. Now when we add them, when we take A minus BK, the resulting matrix is also in the companion form. This is identity, this is 0, and these are the, here we had coefficients A1, A2, etc. up to AN, and along with them what we are getting is these gains K1, K2, etc. So K1 comes here, K2 comes here, K3 comes here, and so on. So we see that the closed loop system matrix is also in companion form, and these are the coefficients of the resulting characteristic equation, the characteristic polynomial of the closed loop system matrix, which is written here. And if we compare this with the characteristic polynomial which is desired, element that term by term, this to this to be compared to this to be compared to this, like this. What we get is, again we get n equations, but these n equations have much simpler structure. They are not coupled. The earlier when we saw in the example, the equations were coupled. These are, each one of them is for a single variable. This Kn plus A1 equal to alpha 1, that leads to Kn equal to alpha 1 minus A1. Kn minus 1 plus A2 is alpha 2, that leads to Kn minus 1 equal to alpha 2 minus A2, and so on. So what we see that we still get n equations, but each of these n equations are in different n variables. One equation is for K1, other equation is for K2, and so on. So they are easily solved. They are not coupled, so they are much easily solved. So the companion form description of the system leads to design equations which are much simpler to handle, and in fact the control gains are difference of the coefficients of the desired characteristic polynomial and the actual characteristic polynomial of the open loop system, and thus we get the control gains. So simple. K equal to alpha minus A. Alpha is coefficients of the desired characteristic equation, A is coefficients of the characteristic polynomial of the matrix, open loop system matrix. So this is what is something to be emphasized, that now the design is easily obtained with the companion form description. So if the system dynamics is not given in companion form, then it can be first transformed in the companion form. A bar and B bar are the system and input matrices for the companion form system, and the transformation which can do is x equal to tz, and this t we know it comes through the controllability matrix. We had seen it earlier. We will do also with the help of the example. And in case of excuse me, in case of similarity transformation, we know that these matrices of the transformed system are related to the matrices of the original system through the transformation matrix. So if we design K bar using the matrices A bar and B bar, which was just described before this, then we can get the K for the original system through this relation, and it comes like this. Because the input u is minus k bar z. Z is the state of the companion form system. So k bar z, and this z is comes from this as t inverse x. So we substitute in place of z t inverse x. So k bar times k inverse t inverse is k, which is shown here. So if we have a system dynamics not available in companion form, it can be transformed into companion form. The control gain can be designed for the companion form system easily, as we saw, and then through this the control gain for original system can be obtained. Now as an example, we consider this system. X dot is this system, which was same as the system shown earlier. So in this system, because it is not in companion form, we transform it to the companion form, and for that we need the controllability matrix, which is this. We set up the controllability matrix B A B A square B. Then we obtain Q inverse, which is this, and we select its last row as some vector V. And then the transformation matrix T, inverse of the transformation matrix, will be assembled. Its first row will be same as this V, next will be V times A, and last one will be V times A square. This was done earlier when we were learning the equivalent transformation, equivalent systems or similarity transformations. So this is V, this is VA, this is VA square, and that gives T inverse. Its inversion gives T, and the transformed system A bar will be T inverse AT, which is this in the companion form. And we compare, we want this as the desired characteristic equation. So the gains for the companion form systems will be obtained as the difference of this and this, which comes as 6 minus 1 minus 3. This is the gains for the companion form system, the k bar. And from k bar we get k by post multiplying k bar with T inverse, and then we get this way. Minus 3, 1, 2. We get the coefficient of the gain matrix of the original system, for the original system, and so we summarize with that. So as we saw, there are two types of feedbacks, the output feedback and the state feedback. And as we saw that even though states were tapped by block diagram manipulations, we saw that through those gains, the state feedbacks, with that we get a block diagram in which the feedback leads to a kind of feedback compensator. In the conventional control, we got a cascade compensator. With the state feedback, we get a feedback compensator. So feedback of states or output is equivalent to a feedback compensator in terms of the classical, if we look at it in the classical way. And we saw that through state feedbacks, all the coefficients of characteristic polynomial can be changed as desired. And this means that poles can be arbitrarily placed at desired locations, of course with the natural restriction of that complex poles must appear in pairs as complex conjugate poles. Output feedback, this is generally not possible. Not all the poles can be arbitrarily placed. And we have also seen that design of state feedback for companion form system is easily carried out. Now as an exercise, I suggest that you can work the same examples which is given here, this system, and you can do the design of state feedback controller with a different feedback, with a different desired characteristic equation. We had chosen s cube plus 6s square plus 11s plus 6. Instead of that, you can take something different. Of course, it should have the poles at stable in the negative in the left half S plane. So that selection can be done, and K can be designed by converting it to companion form or by direct approach. So you can see the difficulty, that how in direct approach we get linear equations, but they are coupled and are simultaneous linear equations, and in case of companion form system we get decoupled equations, or each equation is only containing one variable which can be independently solved. So thank you very much. We will again come across in another lecture.